Am I audible?
Yes, sir.
Okay, right. So in previous sessions, we discussed about bridge trusses, analysis of bridge truss members for moving loads that we have seen. We are analyzed truss members, top chord members, bottom chord member, diagonal member. We are analyzed by using ILD technique. Okay. So now in this session, we will try to discuss about shortcuts to draw influence line diagram for shear, moment, and reaction at support. So these techniques are helpful for your competitive examinations like GATE, IES, and all state government examinations as well as central government examinations like RRB, SSC, AEE, AE, Town Planning Officer, Deputy Surveyor. For those examinations, so these are very important. Okay. So in structural analysis, influence line ILD is a very important technique. So analyzing structures for moving loads. So right, we'll see one by one. So first we'll see shear influence line. For that I am using animated video for easy understanding purpose. So how to draw shear influence line for statically determinate beams we'll see. So what is meant by statically determinate beam? So statically determinate beams are the beams which can be analyzed by using only static equilibrium equations by using only static equilibrium equations. That means sigma fx is equal to 0, sigma fy is equal to 0, moment about any point equal to 0. So that uh, those equations are enough to complete for the complete analysis of the beams. Then those beams are called statically determinate beams. So that means for the calculation of forces in the members and moments in the members, so only these equations are enough. Sigma fx is equal to sigma fy is equal to 0, moment about any section or any joint equal to 0. So by using these equations, if you analyze that beam, then it is called statically determinate beam. What is meant by statically indeterminate beam? Statically indeterminate beams are the beams which we cannot analyze by using only static equilibrium equation, that is sigma fx is equal to 0, sigma fy is equal to 0, moment about any point or any section is equal to 0. For that, additional equilibrium equations are required, additional compatibility equations are required to complete analyzing the statically indeterminate structures. So for that beams we'll use for a complete analysis of that structure, we'll use uh, slope deflection relations and force displacement relations we'll use. Okay. So those are the compatibility conditions we'll use. So now, so we'll see how to draw shear influence line for the statically determinate beams when moving loads moving from one end of the beam to the another end of the beam. So this is, let us suppose this is a river. So to cross this river from A to F, so here we are constructed a bridge structure having a length of beam is one end is A, another end is F. So we are moving load from that situation. How the shear force will vary in the beam? Uh, Shear force in the section will vary. We'll try to see in this session. Okay. So here, first I want to explain about the figure. We have this is a connection at C and connection at E. So here support A, support B, support D, and support F. So we have 4 supports and 2 connections. At C and E, we have a one connection. This is not hinge. This is not hinge. One simple connection. This is not a hinge. So this is a connection, right? So now we'll try to analyze. So length of this is a 4 meter and this is 6 meters. So this bridge is subjected to a moving load. So I want to analyze. I want to calculate shear force at this section C. I want to calculate shear force at section C. So for that, what I'm doing is I'm moving unit point load from A to F. So this is a variation of influence line when unit point load moving from A to F. So then how to draw this shear force at section C when unit point load moving from A to F. If you observe this animated video, when the unit load left of the section C, when unit load of the left of the section C, shear force at section C, shear force at section C is 0 when the unit load moves apart just to right of C, at C is jumps to the 1, then shear at C when the load is moving from C to D, shear at C gradually will going to reduce, and when the unit load at D, shear at C will become 0, and when unit load moves further and further from D to E, uh, the load shear at C will going to increase negative direction, and when the unit load at E, shear is maximum, shear is maximum at C, shear is maximum at C and reaches the maximum value. When the low unit load moves from E to F, the gradually shear at C will going to reduce and the equation comes. So variation of shear force at C when unit load moving from A to F. So we are drawing the variation of shear force at a section C. So yeah, చూడండి ఇక్కడ ఈ diagram మీరు చూడండి. So this diagram will showing shear values at C, at section C, when unit point loaded in this location. Shear at C is represented by here. So shear at C is 0. When unit point load left portion, shear at C is not changing. Up to before just left of C, unit point load left of the section C, shear at C is 0. Shear at C is 0. When unit point load just moves past C, just right of the C, shear at C will become 1. Shear at C will become 1 because we are applying unit point load here. So shear at C will become 1. And then when unit point load moves from C to D, then it is decreases linearly. And when unit point load reaches D, shear at C will become 0. And if unit point load moves from D to E, shear at C continuously decreases linearly and it reaches the maximum negative value, that is 3/2 maximum value. And when once a moving load crosses the E, then it will become again it comes down and it becomes reduced to 0 when unit load reaches F point. So this is the variation of shear influence line for the section C. So when unit load moving from A to F, the variation of shear force at section C we are representing by using this diagram. Okay, when unit point load is moving from A to F, the variation of shear force at section C we are representing by using this influence line diagram. Okay, right. So now, I want to calculate what is the design force for that hinge. So I want to design that hinge. So if 6 kilonewton load vehicle is moving from A to F, Then what is the design force, design shear force for that particular hinge? I calculate. Okay. So if you observe this ILD for shear at section C, at what is the maximum ordinate value? Here it is 1 and here it is 3 by 2. So that means for the design purpose, we have to use this maximum ordinate. That means when unit point load at E section, shear at C is maximum. So we have to consider this load as this ordinate multiplied by this load. That's 3 by 2 multiplied by 6 will give us 9 kilonewton. So 9 kilonewton will be considered for the design of this hinge at C. So for the design of hinge, we have to use design force as 9 kilonewton. So design force we have to use 9 kilonewton. So for the design of hinges, for the design of members, first we'll use so ILD for the different sections. For that section, for the design of that hinge, we are using maximum ordinate developed in the ILD for the shear at C. That ordinate multiplied by applied load will give a design load for that hinge. Okay. So now we will try to see one shortcut method to draw this ILD for shear. So I am taking one simply supported beam. I want to draw shear at section C. Shear at section C. So for that, so this is the we know this variation of shear for simply supported beam when unit point load moving from A to B. So here the ordinate is Z by L and this is L minus Z by L. We are already seeing this one. So variation of shear for simply supported beam, shear at section C. So variation of shear at section C when unit point load moving from A to B. Right, we know this one, we know this diagram. This ordinate is L minus Z. Okay. So then what is the shortcut technique to draw this diagram? We'll see. This is a simple structure. We'll see by using shortcut technique. So for that, what we need to do is we have to at that section. So where we require a shear influence line at that section, we have to cut the section and we need to uh, insert two set of rollers at the section. We have to insert two set of rollers, one left side of section and another one is right side of section. Then we need to apply, we have to apply positive shear force at that cut point. That means, which means left side section, left side rollers we have to apply. For the left side of section, we have to apply downward force, and for the right side of section, we have to apply upward force. So this is positive shear. Left side section, we have to apply downward force, and for right side section, we have to apply upward force. So the deflection of shape of the member will represent the deformed shape of the member will represent the shear influence line. The deformed shape of the member will represent the shear influence line for that section. So this is the shear influence line for that section. So what we did, this is a shortcut for the drawing of shear influence line for any type of statically determined structures. So for that, what we have to do is we have to place set of rollers at this section, and we have to apply positive shear at that section. That means for the left side section, we have to apply downward force, and right side section, we have to apply upward force. Okay. So deformed shape of the member will give the shear influence line for that particular section. So this is the deformed shape. This is shear. So this is the shear influence line for that section C of a member AB. So now I want to draw shear influence line for the overhanging beam. So this is a overhanging beam. Okay. A, B, E. So this is a beam, this is a hinged support, this is roller support, and this is free support, free end. This is free end. So I want to calculate shear influence line. I want to draw shear influence line at section C. So for that, what we have to do is we have to create set of rollers at that section. So pair of vertical rollers I'm placing at section C. I'm subjecting to I'm here at this section. That means for the left side section, I'm applying downward force. For the right side section, I'm applying upward force. So that how does the beam deform? So that deformation of the deformation shape of the beam will represent the shear influence line for that section. So if you observe this figure, so this is a hinge. That hinge will try to move downward direction. Okay, this is a roller. So because of the upward movement of this member, automatically DE portion is also will move downward. So if you up like this, automatically if you up CB member, automatically DE member is also will move downward direction. Will move downward direction. So the deformed shape if you draw, that will represent the shear influence line. So this is the variation of shear influence line for the section C. Then how to calculate these values? So we know this ordinate and know this ordinate. How to calculate these ordinates? So we know the formula for the calculation of negative ordinate Z by L, and this is L minus Z by L. Here Z is equal to AC, L minus Z is equal to CB. So Z by L, AC by L, this distance AC by L plus CB by AB. AC by AB to get this ordinate. To get this ordinate, CB by AB. That is L minus Z by L. Okay. So from similar triangles, so we know this value L minus Z by L. From the similar triangles, we can calculate this ordinate also. From the similar triangles, so this is one triangle and this is another triangle. From these two similar triangles, we can calculate this ordinate. Okay, like that we can calculate ordinates. From that, we can able to calculate so maximum design force for the section C. When unit point load moving from A to B, we can calculate if we given some magnitude, we can able to calculate by using that magnitude. If you multiply with the maximum intensity, you are going to get the design force for that design shear force for that section C. Okay. Now I want to draw for the same beam, but I want to draw shear influence line for the shear influence line at section D. Shear influence line for the section D. So for that was similar same thing. What we have to do is we have to uh, cut this section and we need to place a pair of rollers at this section, and we have to apply positive shear at this section. That means down left side section subjected to downward force and right side section subjected to upward force. Okay, so the deformed shape we need to draw. If you apply left side for the left side section, if you apply downward force, it will not move downward direction. Why? Because this is not a hinged one. This is not hinged one. This is a roller one. So roller will not allow movement here. So this member is also will not move downward direction. So only DE member will try to move upward direction. Try to move upward direction. So that see. So this is a variation of shear influence line for the section D. So this is a shear influence line at section D. Okay, that means when unit point load in between A to D, when unit point load between A to D, the shear at section is 0. Shear at section D is 0. When unit point load reaches the D, shear at section will become 1. This ordinate is equal to 1. And shear when the unit point load in the region D, shear at section D will not change. It will become maximum and reaches to it is unity only. It is reaches the maximum value. The same value will continue up to E portion. So this is the shear variation of shear influence line at section D. Now I want to calculate shear influence line for the cantilever beam. So pair of vertical rods I am applied positive shear. So this is a variation of influence line for section C. So now I want to draw shear influence line for the section E and section E. So first I want to draw shear influence line for the section E. So for that what I'm doing, a pair of rollers subjected to positive shear. So that is the left side section subjected to. So because of this application of force, this will move. So here roller is there, it will move, try to move in this direction. So because of this roller, here one hinge is there. So because of the hinge, if you push this member downward direction, this hinge try to lift like this, try to up, jump like this. Here this is will move in this manner. So this is the variation of shear influence line for the section E. So how can you calculate this ordinate Z by L? How can you calculate this ordinate L minus Z by L? So Z by L is nothing but BE by BC. You're going to get this ordinate. EC by BC. You will going to get this ordinate. Okay. From the similar triangles, we can calculate this ordinate. So from these two similar triangles, we can calculate this ordinate. Okay. I want to draw shear influence line for the section E for this beam. So in that place, what we have to do, we have to place set of rollers and we have to apply downward force to the left side section and upward force for the right side section. And a deformed shape to draw. That is a shear influence line. So that is a shear influence line at section E. So how to calculate this ordinate? Z by L. How to calculate this ordinate? L minus Z by L. Okay. So remaining values we can calculate from the similar triangles. So these ordinates can be calculated. This maximum ordinates can be calculated by using similar triangles. Okay. Right. I hope you are understood little bit. I'll share this video in your course web. Go through this video. If you have any queries, you can ask me. So now I want to. So this is about shear influence line. So now I want to give an idea about reaction influence line. Reaction influence line as well as moment influence line. So now I will share that animated video. Reaction influence line. Reaction influence line for the statically determinate beam. So for the design of these columns, design of the columns for the moving loads, will use reaction influence line for the design of this column members. So these are the column BG and DH. For the design of these columns, we'll use reaction influence line diagram. That means when unit point load is moving from A to F, when unit point load is moving from A to F, the whatever the reaction developed in the member BG, maximum reaction developed in the member BG, that we need to calculate. So for the calculation of maximum reaction developed in the member BG, we'll use reaction influence line, or maximum reaction developed in the DH, we'll use reaction influence line. So for that, we'll move a unit point load from A to F and we'll draw influence line for the reaction for the BG as well as DH. So this is the, if you observe this one, you can observe the variation of reaction in the member BG. So observe this animated video. See, when unit point load at A, reaction at BG is 0. When unit point load at A, reaction in BG, that means the column member BG is 0. When unit point load moving from A to B, the reaction at B is gradually increasing and increasing, further increasing. And when unit point load at C, it will become 0, and again it's changing its sign from C to F, C to E, it's changing its sign, and at E is 0, at F, and it will become 0. At F, it will become 0. So this is a variation of reaction in BG reaction when unit point load moving from A to F. Once again, we'll see. If you observe carefully. Observe this animated video carefully. So that represents a variation of reaction in BG when the unit point load is moving from A to F. Unit point load is moving from A to F. You can even see. Observe carefully. Unit point load is moving from A to B. So this is a variation. The intensity is gradually increasing further. When unit point load C, when it is crosses C, it's and it will become 0 at H, 0 at H, and it is changing its sign. At E, it is become maximum value. When the unit point load reaches the E, the reaction in BG is become maximum, and when the unit point load crossing B, what is E? When unit point load crossing E, then it is gradually reducing. When unit point load reaches the F, reaction at reaction in BG will become 0. So this is the variation of reaction in BG when unit point load moving from A to F. So in this, what is the maximum value while moving unit point load is moving from A to F? So that value we will consider, and that value will be considered, and we'll use that for the design. For the design of that column member BG. So this is a variation of shear influence line, reaction influence line for the member BG when unit point load is moving from A to F. Right. This is the what is the shortcut to draw this reaction influence line? Yeah. First, I want to draw reaction influence line for the simply supported beam. So for the drawing of reaction influence line for the support B, what we have to do is we have to push a unit force. We have to push unit force at B. Then we have to calculate. We have to draw the displaced member. We have to push unit force at B. We have to push unit force at B, and displaced shape we have to draw. So thus the displaced shape, whatever the shape we are getting, that is the reaction influence line for the reaction influence line for the simply support beam B at support B. Means when the unit reaction, so we are drawing reaction influence line for the support B. So how are we going to draw? When unit point load moving from A to B, if you draw reaction influence line for the B, that is the variation. So when unit point load at A, so reaction at B is 0. When unit point load crossing reaching from A to B, so reaction at B is maximum when the unit point load reaches B. So this is the variation of reaction in B, variation of reaction in B when unit point load is moving from A to B. So this is the reaction influence line for the support B. So now I want to draw reaction influence line for the A. So if you want to draw reaction influence line for at A, for that what we have to do, we have to push the member at A at one unit force. Unit force must push and so join the shape of the member. The shape, deformed shape of the member will represent the reaction influence line for the support A. So reaction influence line at A I want to draw. So for this different beam structure. So this is a continuous beam. Here we have internal hinge. So I want to draw reaction influence line at A. For that what we have to do? We have to push unit force at A. So this is the we have because internal hinge. So this is the reaction influence line at A. So I want to draw reaction influence line at C. So for that what we have to do? We have to push unit force at C. We have to push unit force at C. Deformed shape of the member we have to draw. So I'm just pushing unit force at C upward. The deformed shape of the member. This is the deformed shape of the member. So it will represent the reaction influence line at section C or at joint C. It supports C. So now I want to draw reaction influence line for the support D. So for that, what we have to do? We have to push unit force at D. We have to push unit force at D. So this is a variation of reaction influence line for the support D. Right. If you see this reaction influence line for the reaction at A and reaction at B, so this is the variation. Okay. So for a drawing of reaction influence line, what we're going to do is we have to push unit force at that point support A or support B where the reaction influence line we want to calculate. Just to push upward direction, we just apply unit force in upward direction. So whatever the deformed shape of the member or beam, if you draw the deformed shape of the member, that will represent the reaction influence line for that support or support the for that section for the support. Okay. So this is a very reaction influence line for that support D. So here where you are pushing that you have to place that as unity. From similar triangles, you can calculate the other ordinates. It's at B. We have one ordinate, maximum ordinate is there. From similar triangles, we can calculate this ordinate. Here, if we consider this beam, I want to calculate shear influence, reaction influence line at support C. So what we have to do? We have to push unit upward force at C. We have to apply unit upward force at C. The deformed shape is, this is a deformed shape. So we know this as unity. So we need to calculate this ordinate at B. We need to calculate ordinate at B. How to calculate ordinate at B? From similar triangles. From these two similar triangles, we can calculate this ordinate. Right. For the design of this support to see this column, for the design of this column, we'll use this ordinate as a ordinate multiply applied load will give the design force particular column, design force for this particular column member. So we are getting reaction here. Why we are getting reaction here? So we have one column under this one. So because of this column is here, we are getting one reaction. For the design of this column, we'll use this reaction influence line. Okay. Now I want to discuss about moment influence line. I hope you understood a little bit about this reaction influence line. Now I want to discuss about a moment influence line. Shortcut keys, how to draw moment influence line. Determinate beams. So for the design of this member, this continuous beam member, we have to calculate what is the maximum moment developed in the beam. So for that, what we have to do is we will draw moment influence line. If you observe this beam, when the vehicle reaching in the region of C to D, in between C to D, bending moment is maximum at that section. Bending moment is maximum at that section. At G, maximum bending moment is takes place. So now I want to see the variation of bending moment at G by using one animated video. Observe carefully the when a unit point load moving from A to F, when unit point load is moving from A to F, when the unit point load at in between A to B, the bending moment at G is a variation of bending moment at G. So that is when unit point load at A2 in the region A, in the AB region, bending moment is at G, hogging bending moment, that is negative bending moment. Okay, if you observe this one, this is a hogging bending. When when the vehicle in between B to C, the bending moment is going to reduce, and when the unit point load at C, bending moment at G is equal to 0. Here, sagging bending moment is going to develop, and when unit point load at G location, so maximum sagging bending moment will going to develop. If the vehicle further move from G to D, at D location, bending moment at G is 0. Same. Bending moment, if a vehicle at E, bending moment at G is that is sagging bending moment, that is maximum. And when unit point load in the region E to F, the bending change decrease, and it will become 0 when unit point load reaches the F location. So once again, you see this one. So unit point load is moving from A to F. So you can observe the variation of bending moment. So this is a variation of moment influence line for the this particular beam. So this is a variation of bending moment at G when unit point load is moving from A to F. When unit point load at B, the bending moment at G is a negative value, that is maximum negative value. And when the unit point load is moving from B to C, at bending moment at G will become 0. That means unit point load at C, bending moment at G is 0. Moment at G reaches a maximum positive value when unit point load reaches at G location. So this is a variation of moment influence line for the section, moment at section G. When unit point, that is vehicle at G location, maximum positive bending moment takes place. When vehicle at B and E, maximum, so maximum negative values will takes place when the one vehicle at B location and one vehicle at E location will going to do maximum negative value at G will takes place. So by considering this one vehicle in this location, another vehicle in this location, we can calculate maximum negative bending moment at a G. Maximum negative bending. If you want to design that beam, so we have to place two vehicles like this. One vehicle at this location, another vehicle in this location, and we can calculate maximum bending moment developed in the BG, that is negative bending moment. That, and we can calculate maximum negative bending moment. For that bending moment, we need to maximum negative bending moment. We need to design this beam. So to get maximum positive bending moment, we have to place vehicle at a G and we will calculate maximum positive bending moment. So now I want to use shortcut method to draw moment influence line further at a section. So in that section, so for drawing shortcut for a drawing moment influence line at that section, we will follow this procedure. First, we will create one hinge in that section. We will going to create a hinge in that section, and we will going to apply positive bending moment at that section, at that hinge. The deformed shape of the displaced shape of the beam you draw. So that is a variation of moment influence line that section. So first, what we're going to do, we'll create one hinge at that section, and we're going to apply positive shear at that section. That means for the left side segment, we'll apply anti-clockwise force, anti-clockwise moment. For the right side segment, we'll apply clockwise moment. If you draw the deformed shape of the member, that will gives you uh, influence line, bending moment, influence line for the bending moment at the section. Moment influence line at section C. So this is a deformed shape of the member. We are applying positive shear at section C. So this is a deformed shape of the member. So this is a moment influence line for the point C. So this is a variation of a moment influence line for the particular overhanging beam. So for this beam, I want to calculate moment influence line at E. So I've created a hinge here there. I'm applying the positive moment at E. So this is a variation of moment influence line for the section E at a moment at E. When you need to point to moving E. So right, for drawing moment influence line, what we're going to do is we'll place pair of we'll going to place a hinge at the section and we'll apply positive moment at the section. The deformed shape if you draw that will represent the moment influence line at that particular section. Okay. I hope you understood little bit. Go through these videos. I will share in your course web as well as your WhatsApp group. Go through these videos. So these are helpful for your competitive examination preparation. Okay. So thank you one and all. I hope you understood little bit. You have any doubts? If you have any doubts, so you can ask me. I'll try to clarify your doubts. Do you have any doubts? I'll share these videos in your WhatsApp group. You go through those videos. If you have no doubts, you can. If you are not having any doubts, you can leave the session. If you have any doubts, you can stay and you can ask the doubts.